Welcome everybody, welcome to another video on our groundwater cycle class. And now we're switching gear a little bit. So in this past few lectures we've talked about the basic flow equations and how we write them up and what we use basically to deal with groundwater flow problems. Now today we're taking a closer look at hydraulic conductivity, especially when it changes, right? So everything we've done so far, I said, well, K is a constant. We can just take it out of the differentials and not worry about it too much. It's just a number. Well, in reality, right, we have a lot of things that are not really constant, right? So let's start with this left-hand side graph here, or schematic, and that's from USGS somewhere. Okay, so USGS report, right? But you can see that these are just two conceptual representations of an aquifer, where the top one here is K equals constant, what we've done so far. And the middle one here, we have two layers, one of low permeability, high permeability on the top. So this is similar to the leaky aquifer that I was describing in the last lecture. And then here at the bottom, we have, the high permeability on top, and then something with, decent permeability at the bottom. Point being, there's a lot of spatial organizations you can think of, right? Where it's not just all the same everywhere. Actually, there's probably not a single configuration you can think of that is all the same everywhere. So this lecture is really important. It's going to be a little longer than usual. So there's two different topics we'll see today. So one is heterogeneity, and the other one is isotropy and anisotropy. So the first one on homogeneity relates to those pictures on the right here. Where you can see that the sand, this sand on the top, this first sand here is very homogeneous, right? This gravel here is very homogeneous, so it's kind of all the same. Now this formation here is heterogeneous, right? So there's different types of sand, and again, if you remember those pictures from previous lectures, right? So typically we have finer particles going into the bigger pores and so on and so forth, so things are not really homogeneous. Now, if you have these kinds of heterogeneity, typically you can still, and here's another example down here, typically you can still scale up. So there's a scale at which, this heterogeneous media becomes homogeneous, and we'll see this in the next slide. Now, there's another kind of heterogeneity where it is, if you have flow through here, left to right, it goes through a fine sand and then a coarse gravel, and let's say another fine sand, later, right? Now that is also heterogeneous, and it's going to be very hard to average out, but we'll see how we do it. So when we think of heterogeneous media, we typically think of layers of sort of homogeneous things, but that are different. So layer of sand and a layer of gravel, and then a layer of sand, so on and so forth. This kind of heterogeneity from the bottom here is usually ignored, and we assume that we have a large enough volume. So here you can see the homogeneous example of a formation that really is, not very common. Obviously, we've talked about those cubic packing before, right? Now, isotropic and anisotropic are defined here, right? So this is where you have a hydraulic conductivity that is different in the x and y direction. Okay, so if it's isotropic, obviously it's all the same. So this is similar to what we've done before. If it's anisotropic, that means you have a different conductivity, on the horizontal versus the vertical flow. Now here is an example of that, right? These are clay particles, under a microscope, obviously. These are a few microns, size, and you can see that because there are layers, right? If the flow is going across this way, right, it's very different from the flow going across this way, right? It's not homogeneous. Like this guy is the same here and here because it's all the same everywhere. Now, in this case, it's very anisotropic. So you can think of anisotropy as a brick wall. It's similar to that clay particles. So you can see here that we have more porosity this way, or more hydraulic conductivity left to right than you would have, up and down, because now you have to go around those bricks, right? So this is anisotropic, meaning it's different in the x and y direction. And again, we deal with those two cases a little different. So this notion of representative volume, right, that I've talked about before. So if you have that sort of heterogeneous media, but that is mixed, right, well mixed, at some point, so if you measure porosity in small volumes, so let's say here, and then here, you know, and then increasing volumes, right, you'll see different numbers, right? So maybe, you know, you hit like a macropore the first time, so you have a very high porosity, but then maybe you hit, you know, et cetera, et cetera. So as you're increasing that volume, you're sort of averaging out those micro scale differences, and there's a point where, you know, that porosity you measure is sort of homogeneous or constant, so then that defines kind of your domain of homogeneity. So typically we don't really consider these types of heterogeneity in the calculation. We just assume that there's enough volume that this is averaged out. Now here we go. So if we conceptualize the heterogeneity as layers of different hydraulic conductivity Ks, right? So here are 3 layers. Now obviously, depending on if you're flowing across this way or flowing across this way, the way you average those is different, right? So the effective conductivity, hydraulic conductivity, on the horizontal here and on the vertical would be very different, right? So if imagine this K2 here is a fine sand or something very fine, like a silt or something. So imagine you have gravel, right? High conductivity, and low conductivity in the middle. Well, this middle formation here, right, resists flow. So it's not like, you know, the total hydraulic conductivity out is not just the average of those 3, because now you have a resisting layer like an accretard that is not letting flow through. So it's not the same as on the other side, where indeed you have, you know, all the flow here is free to go, all the flow here is free to go, and then this flow here in the middle is, you know, smaller, but then on average, you know, it's just the average of the 3. You take the average of that middle one, the average of the top and the middle, and that's your flow left to right. So it's very different conceptually. Now let's do the horizontal first, right? Well, it's just the average of everything. So all you do is basically calculate Ki, Bi here, right? And then you sum them up and divide by B, and that's your horizontal flow, right? So this is this equation here, right? So the average horizontal flow is just literally the average of, you know, each individual layer, and there's nothing else to it. Now for the vertical flow, this is a little more complicated, so I'm going to try and run through it. So here we're using, again, we're going back to the mass balance aspect, right? So we know that the flow at each of these interfaces must be the same, right? Flow must be conserved. There's the same amount of water going in and out, no matter what. So we're writing Q total, right? So the Q through this whole thing, Q total, must be, again, using Darcy's law, right? The vertical K average that we're looking for, times the change in head, right? This is just the Darcy's law. So the change in head total divided by B total, right? So the DH del B, right? So this must be true, and it must also be true that this amount of water going through must be the same as here, as here, as here, as here. So we can write Q1, Q2, Q3, so on and so forth, right? However many layers you have. Now these Q1 and Q2 here, we can also write the Darcy's law for them, right? So we can say for the first layer, for example, is K1 times del H1 over B1 equals K2 del H2 B2, so on and so forth, right? So this must be true. Now we can rewrite this whole thing as, let me actually clean that up a little bit. Okay, we can rewrite this whole thing as del H total divided by B divided by K av. Okay, let me actually try and clean up some more. Okay, so let's focus on this equation here. Right, so del H total divided by B total. Now I'm putting K average on the bottom here just because it's easier to compare, you know, to the rest of it. We'll use it in a minute. The point is, this is the same as this equation, right? So this guy, we can just, if we say B divided by K here at the bottom is the same as putting K on the top and having on the left here. So it's the same equation, basically. It's exactly the same. This whole square and this whole square here are the same thing. Now, for the same reason, right, we can say del H1 divided by B1 over K1, del HB over K2, right? So we can say that this quantity here equals this quantity here equals this quantity here. Okay, those things are all the same. Now that means that because we know that delta H total, right, equals the sum of them all, right? DH total must be the sum of, you know, H1, H2, H3, so on and so forth. So if we're saying that DH total here equals this plus del H2 plus, right? Now we had equals before here. Right? If we're saying those things here sum to this guy, well, it must be also true that the things at the bottom here must sum to this guy here on the left, right? So if I can sum the numerators, right, to del H, then I can also sum the denominators to the same denominator. So I'm, you know, it must be true that my B over K average here at the bottom, let me again clean that up a bit, right? My B over K average here at the bottom on the left-hand side must be equal to that sum on the right-hand side, just like the top. So if that's true, that means that this is true. That's what I just said. B over K V average equals the sum of all those B over K, right, on the right-hand side. Now finally, I can write my K average, right? So it's 1 over, right, K average. So I'm throwing K average on the right-hand side, and then some BI, KI on the left-hand side, and now I can write finally my KV average, so my vertical hydraulic conductivity, my average, you know, upscaled hydraulic conductivity going through those vertical formation here, is B, the total thickness, divided by the sum of the BI and KIs. So this is a different type of average, basically, and you might remember from some math class, right, the geometric means and the arithmetic means, so this is related, but that's just a demonstration of how that works. So again, the vertical hydraulic conductivity here is not just the simple average, arithmetic average of, you know, all the layers, but it's actually B over the sum of the BI over KIs, and this is how that works. Now, the anisotropy topic, so this is how we deal with heterogeneity. Now, for anisotropic formation, so formation that have different X and Y gradients, right? X and Y hydraulic gradients, or conductivity, and thus, you know, Q, little q, like a Darcy fluxes, right? How do we deal with it? And so you might remember this picture from before, right, where I said that the flow Q is always perpendicular to the equipotential, right? That's what we said when we were doing those piezometric maps, right, and the 3 and 4 well methods. Now here, when we have heterogeneous media, this is not true anymore. We might not have a right angle between the flow and the equipotential. So we might flow sideways, if you will, compared to that piezometric map, right? Now, why is that? Well, if we look on the left-hand side here is a bit of a mathematical explanation, if you will. So again, Darcy flux equals minus K hydraulic gradient, del H. Now, if we look at those things in vector form now instead, or vector and tensors, instead of just the arithmetic or just the calculus, you know, PDEs, differential equations that we've done before, now Q is really QX, QY, right? So it's a, whoops, it's a vector. K is a tensor, right? So now we have K in the X and Y directions that may be different. And then the hydraulic gradient, right, is still in 2D now instead of 1D, right? In 2D, we have the X and Y direction gradients. The angle that the flux, so Q, makes to the hydraulic gradient is given by the arctangent of dH dy over dH dx. So this is again the flux in the y direction, or excuse me, the hydraulic gradient in the y direction and the hydraulic gradient in the x direction, which may be different, right? So now we have an angle, you know, from the horizontal that is given by this quantity here. Okay. All right, let's apply this now. Okay, assume that we have Wellspin Training, and this is actually borrowed from Dr. Baer. I invite all of you interested in groundwater to go check out his book, the Baer 79, and also there's some resources available online at his website, like online classes that are very good. Okay, so assume that wells penetrate a homogeneous, so we're starting with a homogeneous and isotropic case, and then we'll do the anisotropic case to show you the difference. So an isotropic case where the thickness is given 20 meters, porosity is 20%, the hydraulic conductivity is 15 meters per day, so it's probably a fine to medium sand. Piezometric surface between the wells can be approximated as a plane. So again, we have 3 wells here where we can see what the piezometric head is in there. So 8.4, 10, and 11.5. So 11.5, right, is higher. The water is higher than 8.4, right? So we know it's going to go roughly this way. And from 10 here, from 10 here at the bottom to 8.4 again, water is going this way in the y direction, and then on the x direction again, 11.5 is higher than 10, so it's going this way in the x direction, right? So intuitively, we kind of know how it goes, right? Now we can do our 3-well method that we did before, separate everything to get the iso equipotential lines, okay? And then we know that if things are homogeneous and isotropic, right, the hydraulic gradient is here and the flux Q is the same, right? Is also with the hydraulic gradient. So determine the hydraulic gradient, magnitude and direction, total discharge in the aquifer, and the velocity of the water at point P. Okay, so if we solve it, so here's the solution for this first case. So the hydraulic gradient again is composed of dH dx and dH dy. So in the x direction, we're losing 1 meter every 200 meters. So again, remember how you do this. So now the plus 10 equipotential is here. This is the plus 11 equipotential. So in the x direction, right, in those 200 meters, we've lost 1 meter of head. Right? 1 meter of head for those 200 meters of distance, right, of terrain. In the y direction, so same method for the y direction, right? In the y direction, we're losing 1.6 for 200. So again, we have 8.4 here, 10 here, so that's 1.6 meters of head for the 200 meters of terrain. Okay, so that's our gradients. Now we can calculate the magnitude of the hydraulic gradient as, again, this is the hypotenuse of the triangle. So go back to those lectures if you don't remember how to do that. There's the square root of the squared of each gradient, and we end up with the magnitude of it, right? So now we know how much the hydraulic gradient is. The angle, so now we're using that arctangent of the ratio of the gradient. So again, 8/5, right? 8/5 here. And we find 122 degrees. So there's an angle theta, right, to the horizontal. Okay. So here is theta, 122 degrees. You can see this is like 90. So that seems about right, right? It's a little more than 90, so it's 122 when we do the calculations. Now the discharge of the aquifer, right, is KBW del H. And again, this is all given, right? 15 meters per day. W is 20. B is 20, so it's 20 meters deep for a meter of width, right? Per meter of width, and times the gradient here that we just calculated. So if we put all that, that's 2.8 cubic meters per day per meter of width, if you will, right? This is 1 meter width, so it's really a Q prime is the same, right? It's per meter of width. For each meter of width, we get 2.8 cubic meters per day. And then the velocity, of course, is Darcy flux divided by the porosity. So again, K hydraulic gradient, so divided by porosity, and we find that the actual velocity of the water in there is 0.7 meters per day. Okay, so this was the example for the isotropic case. So this is the same as we did for the piezometric maps. Now let's look at the anisotropic case. And I know this lecture is going on long, I'm sorry, but this is an important one. Okay, so now we have different hydraulic conductivity in the horizontal and vertical direction. So 20 meters per day horizontally and 10 meters per day vertically. Now, same question, right? What is the specific discharge? So little q, like the Darcy flux. The angle alpha between Q and H. Okay, so now we'll have a different angle. Now I give you the answers here. So we calculate the x and y gradients the same way. So we have 0.052, 0.05, right? You just use qx equals kx, right? dh dx, and qy, same thing. So we calculate now beta the same way we did in the previous slide, which is, you know, the arctangent of the ratio of the hydraulic gradients. So they're here. And finally, we find alpha, the difference between, so Q and H, right? So H is still in this, you know, the same as before, but now Q is angle. So now we're flowing sideways compared to the general gradient, and we're flowing sideways by 14 degrees. Okay, so this is illustrated here. So this is what we had from the previous slide, right? So this is our hydraulic gradient. This hasn't changed at all, but because now our hydraulic conductivity is different in the x and y direction, is skewed, right? So now we're flowing sideways, and Q is actually flowing here. So this is Q, and of course this is our little alpha. This is our 14-degree offset, you know, compared to the previous slide. So now you can see that the flow, the flux of water is actually not the same, you know, it's not going straight down the slope of the hydraulic gradient, but it's skewed because that hydraulic conductivity is not isotropic. So again, the flow lines and the potential lines are no longer perpendicular. All right, thank you very much. I know this was a little long, but I'll see you on the next video. Thanks.